Hi, my name is Mohit Sarveiya, and my presentation is on writing compiler plugins with Arrow Meta. So Arrow is a library that it's an ecosystem that has different libraries. For example, it has libraries to it has gives you like try and either types, all these different functional types. So the Arrow ecosystem also has a library called Arrow Meta, and that allows you to write compiler plugins much and it provides you with an abstraction to do this. And it's a library that was written about a year ago that's still developing now, and I'm going to show you in my presentation how to write plugins with this library and what is the API that it provides. So um, So in this presentation, I'll show you examples and also how to test those examples. And lastly, you could also, with this library, write IDE plugins, and I'll show you that with an example. So there were two motivations to use this library to explore it, and one is to how do you build tools like IDE compiler plugins, but it also allows you to use many of the Arrow's functional programming constructs like lenses, optics, for example, and it allows you like monad comprehensions also. So it makes it easier to utilize many of the Arrow constructs that already exist, and it has existing compiler plugins in the library that allow you to do this. And so before I talk about the Arrow Meta library, I'm going to share with you how the compiler plugin works. I'm going to share with you the different steps that it has, and we'll look at how Arrow Meta supplements the compiler. So the way the compiler works is that first you need your code that you're going to compile, and you would write it in your IDE. And as you begin to write your code, it gets transformed into a different structure. And this structure is called the abstract syntax tree. And what this structure is that each node in this tree represents some form of some construct in your code. For example, it might be an import statement, it might be a class, a function, or an annotation. And what happens after this gets transformed is that it goes into the analysis phase. And then in this phase, the compiler adds to each of the nodes type information, type semantics for a particular language. So if in this case, it will add it for Kotlin. And in this case is where it will perform type checking. So it will look at, are you like using the types correctly as you should? And when that analysis, if it finds an error, it informs you in the IDE that there is an error. You might see this with a red line, as you see in this case, in this example, and it will give you a message. And if you're incorrectly using types. So what happens in the there is a library called the IntelliJ platform that allows it's language agnostic, and it allows you to specify a lexer and the different tokens and for a particular language. And the Kotlin compiler uses this, and it provides the different keywords in the language and a parser, and it allows you to specify the grammar of the language, and that's Kotlin compiler like hooks into that IntelliJ platform library to be able to parse to convert your code into an AST. So once your code has been type checked, it goes into the code generation phase. So recently there was the back end of the compiler was updated, and it was updated to transform the code into this representation called IR, which stands for intermediate representation. And went from that structure, you could target different platforms, JS, JVM, and native. So when you target any one of those platforms, it will give you an artifact for that. So, and lastly, it goes in, lastly, the compiler is done after going through that and has compiled your code. So when you look at the Kotlin compiler from in an overview, it goes through all these different steps to be able to compile your code. And what Arrow Meta library does is that it hooks into these different steps and allows you to control what happens. So this is a library that was recently last year it was introduced that allows you to do this, part of the Arrow ecosystem. So when you look at each step of the process, there was some art output that was introduced, output that was produced. When the code was written, it went into the parsing step and then it produced an AST. And in each step, there was something that was produced. And what ArrowMet allows you to do is take that AST and to be able to transform it and give it back to the compiler. It allows you to hook into each of these different steps. So, for example, when you look at this code and it gets transformed into this structure, I could with ArrowMeta be able to basically find a particular type of node that I want to transform. It could be a method or class, and I could filter for it and be able to transform it and give it back to the compiler, and then it will move forward in the analysis phase and the code gen phase. I could also hook into the analysis phase where type checking is done. I may have some logic that I want to hook into when type checking is being performed. With Arrow Meta, I could provide a custom type checker into the Kotlin library, into the Kotlin compiler, and I could also use IR utilities. So the Kotlin compiler and provides you with utilities to hook into IR. And this Arrow Meta library allows you to hook into that. So those are the different ways that Arrow Meta allows you to hook into each of these different steps. So now let's look at some concrete examples. So the examples that we'll look at are very simple examples. And these examples are: how do you write a Hello World plugin? How do you write a plugin to be able to determine how long a function took to execute and to be able to log that, to do some logging? How do you also combine transformations and to be able to specify some custom logic in the type checking phase? So let's look at a simple Hello World example. There are two steps that you need to perform to be able to write a plugin. One is the writing out your logic, and to be able to register your plugin. That's the last step. So here's an example. Suppose we have a main method and it calls the hello world method. And the hello world method right now doesn't have anything inside of it. And I want to write a plugin that basically generates this greeting here. And how do I do this? So the way you could do this, first step is to create a variable called hello world, which is going to define my compiler plugin. And it has a type called CLI plugin, which stands for compiler plugin, which is a type alias. So this type alias is basically it's a type alias to a plugin object. And what the plugin object is that it has two parameters. One is the name of my plugin, and the second parameter are all the different ways that I'm going to hook into the compiler. So I'm going to create an instance of this object for my plugin. To do that, I'm going to do it like this. I'm going to say hello world, which is going to be the name of my plugin. So when I do this, what happens internally is that it calls this an operator on a string, which creates this plugin object for me. And this allows you to create your plugin in a nice DSL manner. So the first parameter, hello world, is the name of my plugin. And then inside of the Lambda block, I have things that have the logic of my plugin. So how do we hook into the parsing phase that we need for a compiler plugin? I'm going to use the meta method. And inside of the meta method, I'm going to define a list of extension phases. Extension phases are basically is all the different ways that I want to hook into the compiler, all the different phases of compilation. And in order to hook into the parsing phase, in order to transform a hello world method and give it a greeting, I need to be able to find it in my AST, which is I'm going to use this method here called named function. And I'm going to basically specify what type of function, what function that I want to filter. I could filter by anything. In this case, I'm filtering by name, which is hello world. So when you look at this function, this is part of something called a quote template DSL. So quote templates are basically they all follow this pattern. They have you have the node, which could be a function, a class, and in there you specify what are you looking for, what type of filtering will you do, what type of class or function you're searching for, and it gives it back to you in this Lambda block. So and in there you could specify some transformation you want to do. So when it finds the function, after it has looked into the AST, it will give it to you in this Lambda block, and the type C is a function. The type for C is a function, and I could apply. In my case, I want to apply the replace transformation. So when I apply this transformation, I'm going to specify what is it that I want to apply this transformation on. Is this function? And I'm going to supply to it what the new declaration would be. So I'm using a string template here, and I'm specifying what the new declaration is, and it has a greeting that I want, hello world. The string template needs to get converted into something that's into objects, which is what the function .synthetic scope call does. So here is a very simple hello world plugin, which applies some transformation. And next step is to, after you have specified the logic for your plugin, you want to register it. In order to do that, I'm going to create a meta plugin object. It inherits from a class called meta. You always inherit from that class to register your plugins. What that class provides is a method called intercept. When you look at this method, the return type of this method is a list of compiler plugins, CLI plugins. So I'm going to supply it the list of the plugins that I made, the Hello World plugin in this case. I could supply and register more than one plugin if I want. So when I go and build my plugin for the JVM, it's going to produce a jar file that I could include in my application. So to include this, I'm going to specify basically a compiler option like this. I'm going to give it the path to the jar file of my plugin that I just made. So this is done using compiler arguments. So next step is to run the plugin. And to run the plugin, I'm going to run my plugin with this sample code. Right now, it doesn't have a greeting. So when I run it, it will run my compiler plugin. And then you'll see is that the result you'll get is a greeting called hello world. That means my plugin ran. So this is a very, very simple example of doing a transformation. So let's look at, so the way this works is internally is that it goes into the parsing step. It hooks into that. So the compiler translates this into an AST, and then it hooks into it, and it searches for a node that has this function, kt-name function hello world. And I'm able to do some transformation on it. And I did it, as you saw, replace transformation. So that was a very simple example of a hello world plugin. Let's look at a little bit more of a complex example for being able to log how long a function takes to execute. So suppose you have this function called calculate. It might be, this example is something very simple as taking a list and doing some operation on it, but it might be something much more complex. And what I want to do is that I want to be able to annotate this. And when I do so, I want to be able to log how long it takes to execute, to be able to log what parameter that I pass to it. How do I write a compiler plugin to do that? So what I wanted to do is that I want to generate this code. And what this code does is that it basically logs out. First, it takes the original operation that my function is doing. And what it does is that it logs out what that function is that I'm calling, the parameters that I pass to it. And then it takes in, determines the current time in milliseconds. And then it basically takes my original function body and executes it. And after that, it takes the current time in milliseconds minus the start time that I had calculated previously. What I get now is a time to run, which is, how long did it take from the starting to the ending to executing my function body. And you'll see lastly is that I want to log out this basically this time calculation and return the result. So this is the code that I want to generate for a type of function that has this debug log annotation. So how do I do that? So the way the plugin is going to work is very similar approach to what we saw before with the Hello World plugin. I'm going to hook into the parsing phase. This is going to get converted into an AST, and then I'm going to be able to filter for a particular node. And I want to be able to apply a transformation on it and generate the code that I need. So how do I do that? So I'm going to follow the same mechanics of building this compiler plugin. I have my name of my plugin, which is debug log. And then I'm going to specify different ways that I'm going to hook into the compiler. So in order to do that, I'm going to use the name function method again. And then what I want to do is that when this function, when it gets called, and it will give me the function that I'm looking for that has the debug log annotation that I will apply a transformation on. So how do I specify how to find a function with the debug log annotation in my code? So in order to do this, I made an extension. And this is an extension on a KT named type. So because I'm filtering for a particular type of KT named function object. And in this case, for simplicity, I made it so that I filters for a function that has one int param as a long return type, but it could be something much more general for your use case. And it also filters for the it checks whether the function has this debug log annotation. Let's look at how I implemented that. So in order to determine whether a function has a particular annotation, I made a extension on a KT annotated object. So each annotation you supply to a function gets represented by this method called KT annotated. What I'm giving it to this extension is the name of the annotation names that I want to match. In this case, debug log. So I take basically the strings and I convert it into a set. And what I do is now define a predicate, a lambda. And what it does is that it basically gets the current annotations on the function. So it.typeReference is basically will give me all the different existing annotations that exist in there. Where reference name, I could basically get the current name of the annotation, and I could match whether it is what I want. That is what this predicate is doing. And it returns me either true or false, a Boolean value. So you can see it does it.type reference, and then underneath it, you'll see that it gets the reference name. So it gets me the annotation name that's on the function right now, and it determines whether it's the one that I want. So you'll see in names is a set. So I'm going to run this predicate on that set and determine whether I have any annotations whether it has the debug log annotation. And this will return me a Boolean. So this is a very general way to determine whether a function has a particular annotation. So this is my logic to be able to search for a function that I want, kt name function. I'm going to specify this and give it to this name function object. And then I'm going to apply a transformation on it. So the transformation that I'm going to apply is called replace. I want to be able to now, when I have found this function in my code, I want to be able to transform it and add the logging statement and logging for it. In order to do that, I made a replace method. And the replace method does is takes the kt name function the object that was found and returns a string. The first thing that I'm going to do in order to be able to generate my code is grab the information that I need from the function, which is the name of the function, the parameters that are being used, and also what the current declaration is in the function, what the function is currently doing. So when I do that, I'm going to use that information to be able to generate my code. So I'm going to then specify basically my new function, which is going to be the function name, the parameter name. I'm going to log out what it is, what the current parameters that I'm basically sending. I'm going to then add logic in to do the time calculation, get the current time in milliseconds. I have the original function body, and then I have basically a delta, which is the current time minus the start time, which will give me the execution time. And then I'm going to log that out. How long did the function take to execute, and then return the result. So here is this is what I did code that I want to generate, and this is what my transformation looks like. So in order to apply this, I'm basically going to convert that string into an object, and function is an extension that allows me to do this. And what this does is that it basically converts it into a named function object. And and that will be my new declaration. So then this is what my compiler plugin looks like. So, next step is just like with our Hello World plugin, we need to be able to register it. And I'm going to follow the same mechanics of inheriting the meta object class and overriding an intercept. And I have my list of compiler plugins I'm creating. So the next step is to be able how do I run this? So I'm going to, similar to that as I did before, I'm going to basically include it as a compiler argument. And I want to run basically my compiler plugin on this code. And when I run it with this code, you'll see in the log statement, you'll see it will print out what is the function name that I have my debug log annotation on, calculate, n equal 10 is what I sent. And then it also logs out how long did it take to execute, which is 36 milliseconds. So this is one simple way. You could also, you could extend this to be much more general if you want. So this is a debug log compiler plugin. So next question is how do I test this plugin that it works? So the library, when you look at the Arrow Meta library, it has different modules like for compiler plugins, IDE plugins, and it also has a module which provides you with utilities for testing. It's in the meta testing module right now. So the way you use that is that the first step is to define in your test, your test's going to run on some source code, and you specify basically your input, which is this source code is what it's going to run on. So here is what I wanted to run on. And I have basically my function with the debug log annotation. And the next step is to basically to convert this source into an object, and so that the compiler plugin like could work with it. And code.source is how it does so. It's an extension provided to you. So next step that I want to do is that when I run my tests, I want to match the input with basically the expected output. And I'm going to specify that here. I have my annotation class here, and I'm basically, this is the result that I expect from it. And I'm basically giving it what my generated code should look like. So how do I now, set up my test? So first thing that I'm going to do is to use a class called compiler test. So compiler test is a class given to me by AROMeta. It allows you to set up the scaffolding for your test. You specify in using this class what plugins am I testing. I'm testing my debug log plugin, meta plugin. I specified it here. I want my test to run on some source, which is what I'm giving over here, code equal source. And then I want it to match an expected output, which is what I'm doing here. I'm using the method quote output matches, and I'm giving the expected output that I want to match it with. So what I have done here is that I've specified the scaffolding basically for my test. Now, how do I run this? To run this, the AROMeta library provides me with a method called certThis, and it takes in my scaffolding and it runs my test, as you can see there in the definition there of this function. So I'm going to basically supply that to assert this, give it the compiler test method, compiler test object, and it will run my test. As my test runs in the logs, it will give me useful information on how it's doing so. So the way when I run this test, what you'll see is that it will basically take the source that it's going to run on. It's going to create a KT file, source.kt, and inside of that file, you'll see is that it's going to take basically the contents of it and convert it into different objects, each element of the source. You'll basically convert each element like annotations into a KT named annotations object. It will convert basically in everything like, class decorations, and then it will run your test on this. So these are logs that AROMeta, helpful logs that AROMeta is showing you. So when it runs the test and it gets to the end, you'll see the result. And it will tell you whether the test failed or not, but you'll be able to see what was the generated code when you gave it the source. So it's useful for debugging. So that right there is how you test, compiler plugins. It provides you with the utility to do this. When you look into the library, you'll see many examples of plugins that and how they're tested. So you could check that out. So next thing that I want to talk about is how do you combine transformations together? We saw some of the transformations, so far. We saw replace. How do you do remove? How do you create new sources and combine transformations? So when you look at quotes are different things that you could transform your source code, like expressions, declarations, properties, type reference. We saw like named function is a type of a quote template. So there are many others. Suppose I have in this example where I want to remove this, this greeting. How do I do that? This print line. So I'm going to create a remove plugin just as I did before. And I'm going to search for basically in this method for a hello world function. And then when I get it, I want to be able to apply a remove transformation to it. And the way you do that is that you do transform.remove. You're going to remove this function, and this will be your new declaration. And you'll see is that expression in converts it to a particular expression. This is an extension given to you. This is how my remove transformation looks like. And when I run this, you'll see is that this time it won't print anything to the console because I applied that transformation. There's also something very useful for new sources. Suppose I have this data class and I want to generate new source code in a new file. How do I do that? I have my data class, which is here. Now, maybe I have a use case where I want to generate an adapter to serialize it and deserialize it. So in order to do that, this is what I want to generate. My goal of it is this adapter class. How do I do that? So I'm going to create a compiler plugin and name it adapter plugin. And inside there, inside the meta method, I'm going to have my compiler plugin find a class declaration. And the declaration that I want to find is the one whose name is user. So the name of the declaration is user that I want to find. It could be something much more general, and I want to apply the transformation on it when it finds it. So in order to generate new source code, I'm going to use transform.newSources. So when I do this, what this method takes in is basically, what is the generated source code that you want, and you supply basically your logic in there. How will you deserialize and serialize it? What you get in this lambda block is a KT class type, and then you could use that to basically extract information from what the current class has, and you then specify you want this new source code to be in a new file, which is what this file name, the argument takes in. You have name adapter underscore generated. That's the file name that will be created with this source code. So you could also use transform.newSources to be able to do other types of transformations also. So when I run this code on with that compiler plugin, you'll see a new file generated with the source code that I want, with the transformation that I want. So that's how you utilize new sources. I could also combine transformations. Suppose I have this simple class and I want to be able to change the modifier from public to private. Also want to remove this print greeting method. How do I do both of those things? This is the output that I want. In order to do this, I'm going to basically search for a class called simple class. I'm going to specify two methods. One is to change the visibility. And the way that I'm going to do that is by basically creating this class declaration. It takes in the class that I found, KT class, and it takes in the declaration of that class. And I want to use this information to be able to transform it. In order to do that, I'm going to do a replace transformation, and will be my new declaration here. You can see the modifier is now private. Also want to remove a particular method in there. So I'm going to follow the same pattern, and then I'm going to apply this transform.remove, basically transformation, and this will be the method that I want to search for and remove from the class. When I run this, and how do I combine both of these two things? In order to do that, the library provides a plus operator, and the plus operator basically takes in a transformation that you want to apply, any number of them. It creates basically a transform.many object, which basically takes in a list of transformations. And this is how you basically combine transformations. When I run this will be my result with a private modifier on the class. So these are all the different transformations that you could apply. I recommend using new sources. You could just use new sources to do replace, remove. You could also use it for combining. So I recommend using new sources transformation. Lastly, how do I set a custom type checker? Suppose I have two types, types 1 and 2, and I want to specify, do some custom logic when equality and subtyping happens. In order to do that, I'm going to specify my type checker using this extension called type checker. It takes in a type checker class. So new Kotlin type checker is a class that provided by the compiler in which I inherited, and there are two methods I override, which is one is a subtype of the other. it returns a Boolean, and also for equality. And I could do some custom logic in these methods. So that's how you specify a custom type checker. There are different examples already in the error meta library. There's a type proofs plugin that you can look at. There's one in the community called refinement types, which utilize this functionality. Lastly, the last thing I want to look at are IDE plugins. So far we looked at how to write compiler plugins, but we could use these same concepts to also build IDE plugins to improve the experience. Suppose like I am using some architectural library that's for architecting your app, and it allows you, it might be something related to make, for example, model view intent architecture, and it allows you to set some state. And what I want is that when someone uses my library, I want it to improve, the developer experience when they use it, when they use my APIs. Suppose I want to show an icon in the IDE when the set state method is called. And in order to do this, the way I create IDE plugins is very similar to the way I make compiler plugins. I basically create my IDE plugin object, which is also a type alias. And I specify the name of my plugin, MBI plugin, which uses this operator on a string. And I specify how I'm going to hook into my compiler. In order to show an icon, I have to create a line marker. There's a method called add line marker provider that allows me to do this. What it takes in is basically, the resource, a path to the icon that I want to show. And then it also takes in, I want to show this icon on what type of KT object, KT named. I want to display a message when the user hovers over that icon, which is what message is. And I want to display this icon message on a function whose name is called setState. This is my logic for creating an IDE plugin. So you can look at it, the mechanics are the same. And when I run this plugin, lastly, I want to register this. And I'm going to supply a list of, in this case, my MVI plugin. So when I run this plugin in the IDE, you'll see an icon for whenever set state is called. When I hover over it, you'll see a message. So this is really good for improving the IDE experience when someone uses your library, improving the developer experience. So there are different plugins that exist. There is an optics plugin that was recently merged. There's a lens plugin. There's a plugin for type proofs, and you could check out my blog post on this on my website. I also want to thank all the contributors of this library. And if you have any questions, you could check out these Slack channels. Also, these are some resources I'll link out part of my slides. I want to say thank you for listening. Hope that was helpful. So we have a question: how do you manage imports when replacing functions, function body with functions from another package? So any import that you have there's a KT specific KT object for that, and you could specify logic in there and on how you want to handle that. I don't know in detail on how to how do you manage this when replacing function body, but if you could also ask this question, if you want to, there might be someone else to better answer it in the Kotlin Arrow Meta Slack channel. If you want to learn more, you could check out my blog post on my blog, codingwithmohit.com, which has more information on on error meta. How do you handle for multiple plugin processes with race conditions? That's also a good question. So it will sequentially execute each plugin as you specified in the list in order. But that's a really good question. I also recommend asking that in the error meta Slack channel. I haven't run across race conditions myself. I hope my presentation was helpful.